Hello, I'm Arthur Tisi, CEO of MeaningBot. I welcome you to join me in this brief walkthrough into the math behind our linguistic technologies. MeaningBot provides a combination of a missionary and mercenary focus aimed to help people, be they individuals, in companies, or arrays/teams, understand themselves better and connect with each other on a deeper and collectively valuable level. Thanks go out to Shrishti Rashmi Suresh, a super capable member of our AI engineering team, and Oleg Margolin, who oversees mathematics within MeaningBot, for contributing significantly to this presentation. So in terms of the agenda, first we'll take a deep dive into the technology powering MeaningBot's processes. We'll start by explaining what MeaningBot does and the theory behind it. We'll then discuss the technology we use for our products, and we'll conclude by sharing the insights found through years of research conducted by our experts and many of the most notable scholars in the field. So as an introduction, when we're talking about personality, that's your starting place. Your behavior defines where you go from there. When a person says, wow, their personality has changed, they really mean the person has changed their behavior. Personality is stable. It defines who you are. Behavior can change, and it indicates how you react and express yourself. So personality traits predict patterns of behavior over time. And at its most basic level, personality combines two central factors. The first is, how extreme are your emotional highs and lows? And that would typically be associated with neuroticism. And secondly, how much stimulation do you or does a person need to feel balanced? And that is associated with the trait known as extroversion. These two traits are associated with the Big Five framework. These two central traits are highly biological. Researchers can determine how neurotic someone is by measuring their startle reflex or how much they sweat under pressure. Visual vigilance tests can measure whether a person is exhausted by social stimulation. And so, for example, introverts are more likely to be worn down by that type of social interaction. In support of the biological basis of personality are what we refer to as genetic tendencies. So, for example, identical twins with the same DNA who are raised in separate environments will have similar personalities. And personality is defined as a set of behaviors, cognitions, and emotional patterns that evolve from biological and environmental factors. The personality of an individual can be predictive of his or her behavior in different situations. Personality decides the way he or she would interact with other people, engage in group dynamics, and react in difficult situations. Many companies give importance to all these traits with regard to a new employee in order to determine, for example, how well a person may fit into a culture, perform in a role, address challenges related to problem solving, for example, and many other important parts of an employee's journey within a company. So, for example, there's an abundance of research that suggests that culturally, it's important for employees to fit in order to perform better in a work environment. And these culturally fit employees can be very important evangelists to the overall success of the organization. Quantifying the personality of a prospective hire and then matching it to the existing employees is a great way of assessing if the candidate is a fit, right, for a role, for culture, or for a variety of other things. Finding a candidate who has sound technical skills, good logical reasoning skills, and most importantly, strong emotional intelligence is the best possible combo. And recent scientific literature indicates that EQ, emotional intelligence, stands out as the most important of these three legs of the stool. There are many ways to assess personality. Traditionally, people answer a set of questions under controlled settings. Psychologically, you can then analyze the answers and score the candidate on a personality scale. Assessing the personality this way is time-consuming, though, and it's cumbersome and not necessarily accurate because of subjectivity and bias. These tests are obviously not foolproof, and they can be easily hacked. So MeaningBot has proposed another way to assess someone's personality using the text authored by them. Researchers in psychology have found that the personality strongly correlates with the way people use language. We can make use of this important fact and extract personality traits from candidates' writing. Many experiments have been conducted by psychology researchers to study the effect of personality in the way a person communicates. Experiments have shown that there are significant differences in the use of language based on the personality of the author. If organizations could make use of personality traits derived from text, they obviously could then increase the efficiency of their hiring process. With big companies receiving thousands of applications each day, it's really essential to perform this process with a machine in the loop. That does not necessarily suggest that the machine is the only way with which to engage applicants. There should continue to be a human component. But if we train a machine to automatically learn this task, we can make the process more efficient. So, for example, the process of extracting psychological information from text using a machine would look like this flowchart. It's difficult for machines to understand words and manipulate them. Computers can efficiently deal with numbers. So what we do is we convert words to numbers in a way that carry forward the underlying meaning properly. This conversion has to be consistent, it has to be reproducible, and uniquely decodable in order to be efficacious. Once we encode the text in the format which machines can manipulate, we can extract personality and other traits from it. Moreover, we can analyze language over time and determine behavioral changes and risks or opportunities. And this is what we refer to as temporal analysis. So, what is natural language processing? Well, in its simplest form, it's the domain that studies language manipulation by computers. Natural language processing, often abbreviated as NLP, is demonstrated in this slide, which shows the hierarchy of various NLP techniques developed through decades of research. This is the chronological order of the development of these algorithms. And we're going to take a look into each one of these algorithms one by one and see how each one of them overcame the limitations of the previous ones. So it's kind of a seriatim approach, and that's not to say necessarily that one of the prior approaches cannot be applied today. In fact, we apply all of these approaches in various ways for various purposes. So the first major domain of algorithms is based on statistical methods. So as the name suggests, these methods take into account overall statistics of the text corpus. Some of these methods are more intuitive, and they offer basic words to number conversions. These methods mainly focus on the statistics for the text corpus. Word position number is one of the most basic techniques that comes to mind. Instead of using the words in a sentence, we could just use their position numbers. For example, consider the corpus of two sentences. The dog is on the table. The cat is under the table. So as shown in this table, each word has an accompanying number written below it. It's the position of that word in the corpus. If we have 100 words in the given corpus, the first word would be represented as 1, and the last word would be 100. It's a very intuitive method, and as often is the case, it obviously also would have a fair number of limitations. If we convert, for example, a text corpus this way, we would have an integer associated with each word. As in the example above, we say the is 1 and dog is 2. In the world of numbers, 2 is greater than 1, but in the world of words, dog is not greater than the. Unlike numbers, words are not related to each other by fixed mathematical formulas. So if we build another machine learning system on top of such flawed encoding, it will make enormous errors because of this basic difference between words and numbers. Another problem, one more problem we face, is when a word is repeated. So as in the corpus above, the word the appears multiple times in the sentence. For its second appearance, if we use 1 to represent it again, we lose the sequential information in the text. But if we use 5 to represent it, then we end up having something we end up having more than one representation for the same word, and hence lose consistency. So, to overcome some of the problems faced in the previous statistical method approach, researchers came up with a new theory. One-hot encoding is suitable to use when the entities don't have an ordinal information in them. So as the name suggests, we convert each unique word to a multi-dimensional vector, which has 1 at only one place and 0 everywhere else. The dimension of this vector is the same as the size of the vocabulary of the corpus. So consider the sentence, the dog is on the table. The table here shows the one hot encoded vector. Each row in the table represents the vector for one word. In this case, since we have 5 unique words, the length of each vector is 5. And as we can clearly see, each word is uniquely represented and has no ordinal information embedded in them. This approach faces two limitations. If we have a huge corpus, with, for example, a vocabulary size of 70,000, each word would have to be encoded in a vector of 70,000 dimensions. This leads to an extremely sparse matrix, and hence the matrices' memory consumption is not efficient. Another problem with this approach is that while encoding this, we have completely lost the sequential information of the text. We can uniquely identify each word, but we don't have any information about which words appear next to each other, how many times a particular word has appeared in the text, etc. This approach is seldom used standalone. However, it is a very good starting point for more complex approaches in which sequential information is introduced at later stages. So the bag of words model is a simplifying representation. It's used in NLP and information retrieval. So in this model, a text, for example, a sentence or a document, is represented as the sack or the container or the bag. In essence, it's a multiset of its words, but it disregards the grammar and the word order. But it does keep what we refer to as multiplicity, which, from a mathematical standpoint, is the number of times it appears in the multiset. This approach is a purely statistical approach for looking at text. And in this approach, we code each word by the number of times it appears. So consider the following 2 sentences as our text corpus. The dog is on the table. The cat is under the table. Here you can see what the bag of words or bow representation becomes. Unfortunately, this approach doesn't encode each word uniquely, and it also loses the sense of word ordering. But it does keep a surprising amount of semantic and syntactic content. So this approach is super useful for tasks which require understanding of just the overall tone of the writing sample. But for complex tasks such as personality extraction, this approach is not very helpful. It gives more importance to the words appearing more frequently in the corpus, which doesn't help us. But understanding the words' connection with each other and their ordering is far more important for our purposes. Function words are the filler words of a language. They include pronouns and prepositions, modifying verbs, and the like. That these words fit around the content of a sentence. And researchers in psychology and linguistics argue that the frequent occurrence of certain function words strongly suggest an inclination towards certain psychological characteristics. So, for example, function words as a percentage of a typical vocabulary are very few, relatively speaking, but they are used significantly as a part of somebody's daily communication. So this is the foundation from which, for example, Dr. James Pennebaker of the University of Texas has developed the LUK framework. LUK stands for Linguistic Inquiry Word Count. And there's a notion that if a person says I more often, there's a good chance that he or she is a narcissist. Based on such a premise, psychologists came up with a way to tag words. So, for example, the word I got tagged for narcissism, while the word we got tagged for openness. So, however, although this approach created a pretty good baseline for performance, it is not foolproof. In fact, the use of I, me, we, etc., does not necessarily correlate to a psychological framework easily. Algorithms like this are easy to hack, and hence are not robust for all tasks, which require reliable performance against, for example, system hackers. To overcome the limitations of a number of statistical methods, researchers came up with another way of looking at words. They combined word distributions. And so in other words, by that we mean the frequency of various word occurrences and the semantics of the words, or the meaning of the words. And to accurately and uniquely understand the meaning of a word, it's important to look at the word's distribution and the information hidden in their sequencing. Linguistic researcher John Firth, for example, quoted the premise, "You shall know a word by the company it keeps." All these distributional semantic methods are based on the same premise. So the first distributional semantic method we're going to talk about is word-to-vec. This is one of the groundbreaking aspects of research in the domain of natural language processing. Researchers came up with a way to encode words where each word would be identified uniquely. This model's more complex compared to earlier methods. It has to be trained on a corpus of text. Once the training is finished, it generates a word embedding for each word in the corpus, which can be used in an operational setting. To start training this algorithm, for example, we use one-hot encoding, which we talked about earlier. We build a shallow neural network model, as you see here. And what we do is we feed one word to the model and set the consecutive word from the text corpus as the expected output. At the start of the training, the algorithm makes random guesses and makes huge errors. And what we do is we feed these errors back to the network, and the network learns over time. During this training, multiple passes are made over the entire corpus. The hidden layers' weights in the shallow network are then used as word embeddings. The one-hot encoding brings in the unique representation of each word, and providing it consecutive pairs brings in the sequential information of the corpus. The neural network can then combine the two efficiently to give what we refer to as rich word embeddings. The specifications of the hidden layer are constrained irrespective of the vocabulary size. If the text corpus contains 10 unique words or 40,000 unique words or even 1 million unique words, this algorithm will generate a fixed size vector to uniquely represent each word. Now, one of the drawbacks of this method is that it can't process words which are not part of a vocabulary. This algorithm only understands the words it has seen while training. So if a person makes a spelling mistake and the mistake is trivial, a human would understand the word. But this algorithm can't and will not be able to provide useful embedding. GLOVE is an acronym of global vectors. The inspiration behind developing GLOVE was very similar to that of Word2Vec. Researchers wanted to generate fixed size word embeddings in the vector space. Instead of learning through errors, the network learns through probability distribution. And this approach has two phases. In the training phase, it learns the information from distribution. And in the operational phase, it just retrieves embeddings from the table. GLOVE takes into account the importance of the distance between two words. For example, if the words are right next to each other, they have more connection to each other. But if they have 5 to 6 words in between them, then the effect they have on each other is less. And this is where we're really getting into some very exciting science. To understand the probability distribution, we would build a co-occurrence matrix of all the words in a corpus. So consider the words animals, forest, capital, and king, which would be part of a big text corpus. As you see in the table, the words animals and forest occur together more often than words animals and capital. By going through this co-occurrence matrix, the algorithm learns that animals and forest have more in common compared to animals and capital. And the co-occurrence brings in the sequence of the words. Later on, you'll understand that what we basically do is we create these co-occurrence of words and tie them to a psychological framework in order to understand the relationship between words and people from a personality perspective. The model then maximizes the logarithmic probability of co-occurrences and generates embeddings for each word. This is the step where encoding of a word actually occurs. Each word is represented as a unique vector of fixed size, irrespective of the vocabulary. At the end of the training, this algorithm generates a table. Each row in this table represents a word in the respective vocabulary. Since this table has only those words for which we have co-occurrence information, it is not possible to have an embedding for any out-of-vocabulary word. This algorithm is also not as robust in terms of out-of-vocabulary words and spelling mistakes. A recent approach is fast text. And fast text is a very similar algorithm to Word2Vec. Word2Vec assumes words to be atomic entities. But fast text breaks down those to character n-grams. For example, the word apple is broken down to, say, up to 3 grams. It becomes, right, apple, which is A-P-L-E, A-P, P-P, P-L, L-E, and so on, as you see on the screen. These n-grams are then fed to the same network we used earlier in Word2Vec. This makes our algorithm more robust to spelling mistakes and out-of-vocabulary words and gives more richness to word embeddings. So, for example, we have 2 words in our corpus, Lincolnshire and Lancashire. Both are the names of cities in the UK. Since fast text can see the overlap of shire in both words, it makes a connection between these 2 words and understands that both are related to each other in some way. In the same case, if someone makes a spelling mistake writing Lancashire and writes Lancashire, Lancshire, the embedding offered would still be closer to the word Lancashire, and hence give us robust and deeper understanding. Since we are breaking down every word to multiple n-grams, the time taken to train this algorithm is significantly more than the time to train Word2Vec or Glove. And a major drawback of distributional semantic methods is dealing with the problem of polysemy. Polysemic words are the same words with different meanings. And since these algorithms give us only one embedding per word, it can't differentiate between polysemic words. To resolve the problem of polysemy, we need to understand the context of the words. So, for example, the meaning of the word book is very different in these 2 sentences. John was reading a book. John planned to book a flight for his travel. John was booked in court, whatever. To understand the differences in meaning, we've taken into account context of the sentence. And so, hence, we move on to what we refer to as context-based semantics. So in terms of context-based semantics, ELMO is an acronym for Embeddings from Language Models. It's not the Sesame Street character, although I wish it were. This method uses a variant of recurrent neural networks called bidirectional LSTM networks. These networks have long, short-term memory. And hence can generate word embeddings based on context of the focus word. So long short-term memory means the network can remember many short-term connections. These LSTM networks are way more complex than neural networks explained earlier. They have feedback loops passing through time layers, and that is how they generate memories. ELMO looks at a text sample from both forward and reverse directions. So since LSTM has the capacity to remember short-term dependencies, when we feed a word to the network, it looks at words that precede it and also that proceed it. ELMO assigns an importance factor to each word based on their distance from the center word. And based on this importance factor, ELMO combines the embeddings of preceding and proceeding words with the center word. This is how the context information is included in the final embeddings. ELMO has 2 parts. One, which looks at words in the forward direction, and the other one, which looks in the reverse direction. The forward part looks at the center word and 2 or 3 preceding words to predict the next word. The reverse part looks at the center word and 2 or 3 words preceding it, and then predicts the word appearing right before the center word. Elmo stacks layers of encoder LSTMs and decoder LSTMs on top of each other. Each layer has two parts, forward and reverse. Each forward and reverse part have encoders and decoders. These encoders and decoders are connected in a series to convert words to numbers and back to words. The output of these encoders is hidden in the network. And this hidden output is the word embedding we would extract out of the algorithm. Elmo can only look at the text in reverse direction in training mode. When in prediction mode, it doesn't have the access to the future words, and hence does not look at words in the reverse direction. In prediction mode, Elmo looks at preceding words to generate embeddings for the center word. If Elmo was given these two sentences we looked at earlier, for example, John was reading a book, John planned to book a flight for his travel, it will generate different embeddings for the word book based on the context. Yeah, it is kind of fun that the next acronym, based on a distributional semantic approach, is also based on a Sesame Street character. This one is called BERT. But BERT is an acronym for bidirectional encoder representations from transformers. BERT also uses the BIL STM networks as a main building block. BERT is trained to build a word prediction model. This approach is a bit convoluted, right? BERT is trained to solve the exercise of fill in the blanks. So this could be used, for example, to determine the completion of an essay, or to determine the credibility of somebody generating an essay, for example, at a university. And ultimately, you could use this technology, for example, to compare that based on an analysis of personality. While learning to do this task, it develops a good understanding of the words. We extract this understanding in terms of numeric vectors as word embeddings. BERT also looks at text in forward and reverse order in training mode and uses only forward direction in deployment mode. It's very similar to Elmo in architecture, but in place of encoder-decoder units, BERT only has encoder units. Both Elmo and BERT are giant models with hundreds of millions of parameters to be trained. They require substantial amounts of text data to train on, and they also solve problems of polysemy in that they embed statistical and sequential information. Okay, we're finally at the end, and we presented here the history of natural language processing spanning over a long period of time. As the research in this field progresses, the techniques are becoming more sophisticated and accurate. Now, at MeaningBot, we're using many of these techniques to serve different parts of our overall process. And we're staying on top of this area so that our research is up to date and in line with the changing language of millennials, for example. And we apply our science to various languages. So when we build these psychological models based on NLP, we build them based on the native language. So, for example, we don't build a model in English, then build a psychological framework around the English language, and then convert another language to English and then derive the same results from English. Every time we build one of these things, it's built on the native language using the various approaches. And so you can understand how the algorithms work together and how our IP starts to come together. So, in essence, What that means is our goal is to apply the right tool to the right task, combining where we can for optimal results when combined with another level of additional machine learning and statistical techniques that we deploy underneath the NLP. And the end result, we believe, is a superior approach to this science, whereby MeaningBot is always advancing the latest techniques and adding to our algorithmic frameworks so that, for example, when a new framework comes up, we can then append that framework to the work we are already doing. Okay, thank you so much for being part of this and listening. Hopefully you've learned something. We welcome feedback. Thank you especially to Shrishti Rashmi Suresh for her invaluable contribution to this work. And MeaningBot thanks you all for joining us and understanding technology that and the technology that's empowering our success, but more importantly, our passion to better understand and assist the world in their pursuit and understanding of meaning, and their pursuit and understanding opportunities that are presented to them in their lives. If you have any questions, please feel free to reach out to us at the email below, theteam@meaningbot.com.